Today we're going to talk about checking model assumptions in regression. So far we've talked about how to fit multiple linear regression models. We've talked about things like hypothesis tests, variable selection, but all along the way is embedded for all this to be valid is that the data actually follows the model, the assumptions made in our regression model. And so first, let's remind ourselves of what those assumptions are, and then we're going to look at how we can make some plots to assess those assumptions. Okay, so let's call this topic checking model assumptions. Okay, so let's first remind ourselves what those assumptions are. Okay, so here's our multiple linear regression model again in general. So we're modeling a vector of responses, y, as a random variable. We think of it as this linear component. Okay, so the variables in x, and then you have the parameter vector. So it's linear in the parameters beta. Okay, and then plus the part that is not modeled. So by this deterministic linear part. Okay, so we have this vector of random noise, deviations from the linear relationship. Okay, and what did we specifically assume about epsilon here? Okay, so epsilon, we assumed through all the derivations we've done that it has a multivariate normal distribution. Okay, so errors mean 0, and then each of them has independently distributed with variance sigma squared. Okay, and so we can express that compactly as sigma squared times identity matrix, and specifically it's n by n with n observations. Okay, and so what does this imply about specifically? What are the things we need to check about epsilons? Okay, so practically, what does this mean? Okay, so let's make a few points about that. This means okay, so another way of expressing this is that each of the errors is in using a term we previously introduced, or ID, independent and identically distributed with normal distribution, mean 0, sigma squared. Okay, so that's equivalent. And so, okay, so what do we have to check then? Okay, so we have a few. This leads to a few assumptions. So firstly is that all the errors are independent. Okay, so independence among all the error terms. And furthermore, they are normally distributed. They are okay, so they have a normal distribution. And they have mean 0. Okay, so what does mean 0 here suggest? Well, remember that the model says, okay, so since e of yi, okay, so you can write that in the writing out the linear part. Remember, it looks like this: so beta 1 xi1 to beta p xip. Okay, so this is implied since we want the mean of epsilon I to be 0 is implied by so 0 mean error. Okay, it implies that on average y is correctly described by this model. Okay, so so for any values of the x's, so xi1 up to ip. So what this is saying is that this linear relationship correctly describes what's going on in the responses. All the individual errors have the same variance and standard deviation. Yes, so according to the model setup, the way we started out, we say epsilon I has the same mean, 0, and the same error variance, sigma squared. Okay, so no matter what x's you plug in, and no matter how big the expectation of the response is, the basic model assumes that the amount of variability around the fitted regression line is the same. Okay, no matter where you are on the graph. Okay, so for any values of predictors, the linear, on average, the linear model correctly explains the response. So the linear model is appropriate in the sense that it correctly explains the response on average. Okay, so that's 3, and then I'm just missing one last one, which is, yes, as pointed out, they all have the same sigma squared. So constant error variance, sigma squared. And so that has to be true no matter what values of x you plug in, and no matter where you are in the plot as far as expectation of the response is concerned. And we'll quickly see some examples later today where this can be easily violated. Sometimes the error will increase, for example, with the expected response. As we'll see later, one of our first simple linear regression models we fitted was Florida oranges. Okay, so the amount of output versus the number of acres used to plant oranges, and you might imagine that when you fit the regression line, well, the larger the farm or the larger the county, probably the more variability there is around the regression line. So that would be an example of non-constant error variance. Okay, so these are the 4 things that we should check after we finish fitting a regression model to make sure that none of these are egregiously violated by the data sets that we're considering. Okay, so slight problem is, well, we actually don't get to observe what these epsilon i's are. Okay, so let me connect these error terms with the things that we actually observe, which are the residuals. Okay, so let's first make that connection. Okay, so let's first say we could assess these assumptions. Okay, so we could look at so the key idea here is, well, if we had the epsilon i's, we can look at them and see whether those values and see whether these 4 things are reasonably satisfied. But we actually don't get to observe the epsilon i's. Okay, so via the epsilon i's, but we can't observe them because they are given by this theoretical model. But instead, we observe something related, which is the residuals. Okay, so we can't observe. We can observe epsilon I directly. Rather, we have an approximation. We do have approximation via the residuals. Okay, so that's why we have a different notation for the residuals. Here I use epsilon for these error terms, but we use EI for the residuals. The residuals, so we call them E sub I from the fitted, which we can calculate from the fitted model. Okay, so remember the residuals are you take the actual yi and you subtract the fitted value for it, mu hat. Okay, so this is going to be related to something I asked you to do on the second assignment. In particular, in the second assignment, you looked at the relationship between the residuals EI and the fitted values mu hat I. Okay, and so we're going to use that relationship to explain what's going on here. Okay, so we do have that approximation, so let's explain how that's the case. So recall we have this relationship that the residual vector, as we previously showed, is multivariate normal distributed, mean zero, and the covariance matrix is identity minus the hat matrix times sigma squared. Okay, and so you can see right away that there's a difference, right? So the theoretical error terms are mean zero, and then variance is sigma squared times identity. But then what we actually can observe is the residual vector, which is also mean zero. And in fact, by construction, the sum of the residuals, as we showed earlier, so if you add up all the residuals, that is zero by construction of least squares. And the covariance matrix is slightly different. So you do have the identity times sigma squared, but we have to subtract off the hat matrix from it. Okay, so this is not going to be not quite equal to the identity. So the distribution of the residuals is going to be a little bit different from the distribution of the underlying unobserved error terms. Okay, so so what is H? That's the hat matrix, which you have used previously, where H is the hat matrix. Okay, and so we see that these two are the residuals, and epsilon are related. Okay, so let's look at specifically how to relate them. Okay, so E and epsilon are related. Okay, so let's crunch through a little bit of linear algebra to show that relationship. Okay, so what is the residual vector? Well, we know by definition is to take the response vector, and then we subtract off the fitted values. So you have x times beta hat. And we already showed that this is in fact equal to identity minus the hat matrix times y. Okay, so let's expand this and see what's going on. So let's substitute what y is. So according to the models, I'm going to plug in x beta plus epsilon for y. Okay, and then let's expand and simplify it. Okay, so let's multiply this, do the matrix multiplications. We'll have four terms. So I'm going to group them like this. So we're going to have an x beta, and then we're going to have a minus hat times x hat matrix times x beta, and then we're going to have I minus identity minus hat matrix times epsilon. In fact, this first part is 0. Okay, so this actually is 0. So note, so you can easily check that the hat matrix times x is simply x, because once you write it out, we'll notice that one of the x transpose x inverse cancels. Okay, so hx is just x, so this first term disappears. Okay, so therefore we have now seen that, so in the end we get identity minus hat times epsilon. Okay, so therefore we can express the relationship explicitly between the residuals which we observe, and then the underlying error terms epsilon in the model which we don't observe. Okay, so in particular, it actually is related exactly by this quantity identity minus h. Okay, and so the key idea here is that this residual vector can be thought of as an approximation of the true unknown errors. Okay, so I need to clarify something that here, for example, if you look at this equation, I mean it looks kind of funny that, okay, I can write the residual as I minus h times y, and it's actually the same thing as, well, I minus h times epsilon. Okay, so what's going on here? Does that mean like y is the same as epsilon, or does that mean that I can solve epsilon from the residual vector and this matrix? Well, the answer is, well, actually no, we can't. And so let me explain why before we move on. Okay, so note. Okay, so this is a side note that Okay, so first thing to note is we can't actually solve. Okay, so I'm going to put solve here. So we can't actually use this relationship to solve what the epsilons are. Okay, so why not? Well, because this matrix I minus h. So you know if this was invertible, then you simply invert it, and then you can solve epsilon in terms of the residual. But you can't. Okay, so why is that? Because I minus h is not invertible. Okay, so we can't solve since we can't invert I minus h. Okay, well, why can't we invert it? Well, because it's not it is not full rank. Okay, and so to realize that, let's remember that both h and I minus h are idempotent. And so their rank is determined by the trace. Okay, so we know that the trace of the hat matrix is p plus 1, which is also the rank of the matrix X. And so if you add the identity to it, so you would have n. So this trace of the identity is n. So the trace of I minus h would be n minus p plus 1, which of course this is not full rank. It's less than n. Okay, so and so therefore we can't invert I minus h. So that explains why we can't from the residuals we cannot recover epsilon. Likewise, we can't. That also explains why epsilon and y are. This doesn't imply that y equals epsilon. Okay, so similarly, this does not imply y equals epsilon. Okay, so that's because of this property on I minus h. Okay, so that's just a side note. So they're related, but they're not. They're not. Cannot directly recover epsilon from this relationship. Okay, so now let's talk about specifically how this relationship. So if I want to write this out, so it's currently in matrix and vector form. So I want to write it out, then I can do each entry I can write like this. Okay, so an individual residual. Okay, so just to multiply this out, so I'm going to have the identity times epsilon. So I'm going to have the epsilon I. So it's going to have some correspondence, but it's going to but I'm going to subtract this multiplication of h times epsilon. And so, okay, so what is that? Well, that means I have to sum over the matrix multiplication of h times epsilon. So I'm going to have all the, so it's going to look something like this. Then I take the entries of the hat matrix summed over epsilon j. Okay, so that's what it's going to look like. So you notice the residual is equal to epsilon I minus some stuff. Okay, so what we see from this relationship is which means the residuals is a good approximation to epsilon I when the entries. Okay, so these entries hij of hat matrix are small. Well, I mean, in practice, often that is the case, and we're going to see the role later of these entries of the hat matrix in determining, for example, when we have outliers, which we'll define and talk about how to deal with in a couple lectures time. Okay, and so usually this is so I'll say which is put in quotes, just very informally, which is usually the case, especially when you have a large sample size. Okay, so that's pretty informal, but that'll be sufficient for our purposes for now. Okay, so what is the distribution of an individual residual? So let's look at that briefly. Okay, so I wrote here epsilon is the vector is multivariate normal, mean 0, and then this I minus h times sigma squared. So from here, this implies, okay, so this, so an individual residual therefore has a normal distribution. Okay, so remember that's a property of the multivariate normal. When I take individual elements of it, it's going to be normally distributed with the corresponding variance in the diagonal entry of this covariance matrix. Okay, so an individual residual will have mean 0, and it will have variance given by, well, what's on the diagonal? Well, it's the identity, so it's going to be 1 minus that diagonal element of the hat matrix. Okay, so it's going to be sigma squared 1 minus h sub I. Okay, so that's the distribution of an individual residual. So again, you notice that this is slightly different from the distribution of epsilon I, which would simply be sigma squared. Okay, so there's this adjustment factor here, right, based on the hat matrix. Okay, so again, this confirms the earlier point. If the elements of our hat matrix, okay, remember the hat matrix is positive semi-definite, so therefore the diagonal elements are non-negative, so it's going to be 1 minus a small number, a small positive number. Okay, so it's going to be close to sigma squared often, but it's going to differ by a small amount. And so, okay, so this is a normal distribution, so we can standardize it, so this in turn means that I take EI, so minus the mean, that is just 0, and then divide by the standard deviation, so 1 minus HII. So this is the normal 0, 1 distribution. Okay, and so so this sort of expression looks a little familiar to us because we can and when we're doing hypothesis tests on beta, for example, we're going to have this unknown sigma in the bottom, and so what we do is we plug in sigma hat for it. Okay, so we could imagine doing the same here. So if we plug in, the estimate sigma hat into this expression, that's how we define that what's known as the studentized residuals. Okay, so specifically it's called DI, and how we get them is I take this expression, so I take each residual and then I divide it by sigma hat. Okay, so plug in our estimate for sigma, and then 1 minus H sub II. Okay, so what this does, as you can see, is it ensures that it basically standardizes the variances of based on this expression. So it gets rid of this 1 minus H sub II factor. Okay, so we will see how these are specifically useful later in helping us detect, for example, outliers in our data set and influential points, and we will come to that in a couple lectures. But it's good to have that definition. So then we see that we can indeed adjust for these differences in the variances of the residuals. Okay, so with that said, for practical purposes, it's good enough, at least it's standard practice, to check our model assumptions simply using the residuals, EI. But it's also, of course, possible to use these studentized ones, which get rid of this 1 minus HII term. Okay, so let's now move on to how we actually use the residuals. Okay, so the common practice is to use the residuals, to use the residual vector for the model diagnostics and the plots that I'm going to describe to you. Okay, so for the following residual plots and diagnostics, so I just put it in brackets here. While it is also, we can also use DI. Using the studentized ones is also possible, but we'll focus more on the DIs when we come back and talk about influential observations. Okay. Okay, so we're going to next run through a series of plots that we can make to assess whether those 4 model assumptions that we started with are reasonable. Can I move the camera? Okay, sure. Okay, hopefully that's a little better. Okay. All right, so now we're going to show how we can use following residual, to assess, to check model assumptions. Okay, so let's run through the list of plots that we can make based on the residuals, knowing that they are usually a good approximation to the underlying errors, the epsilons. Okay, so the first one is to plot the residual vector versus the fitted values, so it's mu hat. Okay, so this should look familiar because I asked you to look at the distribution jointly of the residual vector and the vector of fitted values on your last assignment. Okay, and so something I hope you found was that in the assignment, we walked you through a means of proving that the elements in each of these vectors are in fact independent. Okay, so in your assignment, you showed that the elements in the residuals and the fitted values are independent, are mutually independent. Okay, and why are they mutually independent? Because the covariance between any epsilon I and any mu hat j, you would have shown is 0. Okay, and so since they are part of a joint multivariate normal distribution, that means they are independent. Since multivariate normal distribution with covariance 0. Okay, and so I asked you to think about, well, if you make a scatter plot of all the pairs, so epsilon, EI and then mu hat I, and you make a scatter plot of all those, I asked you to consider what that might look like. Okay, so now let's draw a picture together. Okay, so first I'm going to draw a picture of what's considered a good residual plot. And then we're going to look at examples where the residual plots suggest that there might be problems and violations of our model assumptions. Okay, so first let's show kind of a typical example of a good scatter plot. Okay, so this we'll call this typical good scatter plot. Okay, so what is it going to look like? So I'm going to here. Okay, so this is 0 on the axis. So over here I'm plotting the residuals, and then here I'm plotting the fitted values. Okay, so we're going to have a scatter plot of them, and we know that they're mutually independent. So what it's going to look like? Well, we know that the average residual is 0. Okay, so that's why I'm putting this 0 line here. And so what you're going to end up having, if if there's nothing wrong with the model assumption, is that it's you're going to see a random scatter around the zero line. Okay, so it has no visible patterns. Okay, so no visible patterns, and so random scatter, and this scatter doesn't change as you move right. For instance, you don't see any trends. You don't see any like funnel shapes. So this is a good scatter. This is a good scatter plot. Okay, so this suggests no assumption, no violation of this fact. Independence of E and mu hat. Okay, so that's a good scatter plot. So, for example, if you were to fit a regression line through this plot, then it should have, well, it's going to have no slope. Okay, so there's no visible trends, and it's going to have an intercept of 0 because the average residual is 0. Okay. On the other hand, we could see we can use the scatter plot to identify various problems with our model assumptions. Okay, and so here is a typical example. Okay, so here's an example of a problematic scatter plot. Okay, so let's again set up the fitted values and then the residuals, here 0. Okay, so suppose the variance around the 0 line here is fairly small, and then as you start to get further out, you notice that the amount of variance increases. So you can kind of see this kind of shape here. So this is an example of a scatter plot between fitted values and residuals that reveals that some model assumption has been violated. Okay, so which one? Well, it appears that the variance is not constant as a function of fitted values. Okay, so this shows. Okay, so this is an example of a bad scatter plot because the variance of the residuals is not constant. In fact, it increases as a function of the fitted values. Okay, so higher. So this is a fairly common situation that can arise. So the variance increases with the size of the fitted values. So it increases with fitted values. So higher fitted values have a higher variance. More, in other words, in terms of the regression line, there's the scatter around the line is wider when you have larger values. Okay, so all right, so that's the first plot that we can make, and so in general, this plot of E versus mu hat can show at least some possible violations, if they exist, can show deviations from independence and the assumption of constant variance Okay, so those are two things that we can that this residual plot could show. Okay, can show deviations if those assumptions are violated. Okay, so that's the first plot we can easily make based on the fitted regression model. Just extract the residuals, extract the fitted values, and then that can give us a visual assessment of whether there is problems with the corresponding assumptions, independence, and also that the variance doesn't change as a function of the fitted values. Okay, so second kind of plot. All right, so we can plot residuals versus fitted values. We can also plot residuals versus the individual predictors. Okay, so there's another type of residual assessment plot. We plot residuals versus the individual predictors. Okay, so we call them xj. Okay, for each predictor. Okay, so you have j of them, then sorry, you have p of them. You can make p separate plots for each of them in the model. Okay, and the rationale for this kind of plot, okay, is that especially if your model doesn't have too many predictors, this might help us detect if there is non-linearity in the response versus that particular predictor. Okay, so let's say when not too many predictors, this can help detect. Non-linear relationships. Non-linearity between the x, that particular predictor, and the response, y. But of course, it's not going to be as practical. We're dealing with a large number of predictors. It's not as practical when p is large. Okay, so let's just make that point. Okay, so when there are no problems, again, what should we expect? Well, epsilon and xj, well, there should be no relationship between these two. And so again, this is your typical good scatter plot, except you would now have xj here on the x-axis. Okay, so keep in mind that this is the kind of scatter plot we're looking for in both of these situations. Example of a good scatter plot. Okay, so I'm just going to save myself a little bit of drawing. So I'm just going to give you an example. So the same idea. Okay, so I plot that predictor on the x-axis. The residual should be randomly scattered around it. Okay, so as typical good scatter plot is analogous to previous, except now the predictors xj is the x-axis. Okay, so we're looking for a random scatter. Good random scatter is good. Okay, so, well, how can we sometimes see nonlinear relationships from a plot like this? Well, okay, so here's an example. Okay, so of non-linearity detected by the scatter plot. Okay, so imagine you have data that is where x and let's say xj and y are not linear, and so for example you have, for example, the relationship might have this sort of form. Okay, so it's, you see there is a relationship between x and y here, but it's not linear. Okay, so if you fit the regression line, it might look something like this. Okay, it might look something like this, and so what you'll notice is in this nonlinear relationship, you look at the residual, so the difference between the points and this fitted regression line, there's going to be a systematic pattern. Okay, so what is this going to look like? So the corresponding residual plot. Okay, so you're going to notice some systematic patterns, right? Because when xj is small, you tend to have negative residuals, and then in the middle you have positive residuals and you have negative residuals. Okay, so when there's an egregious violation, then you will see a very strong pattern on the plot. Again, we're not looking for, if there's just a few points and it's not super obvious, then we shouldn't be too worried. But if we see systematically that it's very egregious, then that's something we probably want to deal with. Okay, so what is this going to look like? So let's draw here. So we now plot the residuals as a function of this predictor. Then you're going to have negative residuals, and then it's going to have positive residuals, and then you're going to have negative residuals. So that's basically what it's what we see in here is there's a trend of the residuals as a function of the predictor. Okay, so that suggests that there's some nonlinearity going on. Okay, as my first regression professor once said, I mean, if the residual plot frowns at you like this, then you need to perhaps do something to fix it. Well, likewise, if it smiles at you, in this case, it's not necessarily good either, because that would also be a nonlinear relationship. Okay, so this plot can help detect nonlinearity between the predictor and the response. Okay, so that's the purpose of that's one purpose of assessing the assumption of linear relationships in the model. So that was where the expected value of, we know by construction the sum of the residuals is 0, but we do want to check whether for any particular values of x, whether the expectation of y is actually on the line. So you see here, for example, when xj is this value, the expectation of y is here based on the model, but then the average error at this value of x, they're all positive. Okay, so therefore that is a violation of the assumption that expectation of epsilon is 0. So let's just make a note of that. So for example, so say here is expectation of yi. So then this cloud of points shows us that, so from here we know that expectation of epsilon I is actually positive for that value of xj. Okay, so therefore that's how we know from this plot that we have a model assumption violation, in particular that model assumption of linearity between x and y. Okay, so again, like if you have a lot of predictors, this might not be too practical to check, but if you're dealing with smaller regressions, this can be a useful tool as well. So to plot the residuals against the individual predictors, again, we're looking, the ideal case is where you have a random scatter that looks like this. Okay, so that's our second type of residual plot. Okay, and then third one is that if okay, so this one is specific and doesn't always apply. So if the numbers in the observation number, so the observation numbers in the data set, so in other words, 1, 2, up to n, were collected in some order. So it's not just, so when I say some order, so for example, they were collected from over time. So for example, observation 1 was collected first, 2, and then up to n. So from in terms of time order, or for example, space order, time or space. So in other words, if there is some meaning behind the order in which the observations are shown in the data set, then we also can do a corresponding scatter plot just to check whether there is dependence according to this, using these indices 1 to n on the x-axis. Okay, so we also can plot EI, so plot the residuals versus the indices I. Okay, to check for any patterns. So again, just like in all these residual plots, we're looking for random scatter. Okay, so that's the ideal. In other words, to summarize, the ideal residual plot is always random scatter. You don't want to see patterns with respect to the fitted values, with respect to the predictors, and also with respect to the order in which if relevant, the order in which the observations and data were collected. Okay, so those are 3 sets of residual plots. So what haven't we addressed yet is the assumption that the errors are normally distributed. So that's the next one. So okay, so how do we check whether a bunch of values are normally distributed? Well, first thing we can do is we can start with a histogram. Okay, so you can look at a histogram of the residuals. Okay, and so they should be normally distributed. So at least the histogram should show, well, if what's consistent with a normal distribution. Okay, so so you can ask things like, is it bell-shaped? And what else we know is and symmetric. So we know a normal distribution is symmetric. Okay, so this is to assess normal assumption. But the histogram is really just a really rough visual for that. And so, I mean, things can be roughly bell-shaped and symmetric, but not necessarily normal. Okay, so for example, you might have fat-tailed or a thin-tailed distribution, and the histogram, it might not be obvious from the histogram. And so we do have a different kind of plot, which can more easily detect violations of normality. And the one we'll focus on is called the quantile-quantile plot. So let me introduce that to you. Okay, but the histogram can't easily detect, for example, overly fat or thin tails. Okay, so a more formal plot is the QQ plot. Okay, so this is the QQ plot of the residuals. Okay, so this is quantile plot. So that describes how the plot is designed to match the quantiles of two distributions. Okay, so this more formally assesses normality, and we can more easily pick up, more easily detect violations to normality. Okay, so first let me describe what it is, and then I'll draw a bunch of pictures to show examples of what we can see from quantile plots. Okay, so what is it? So it is a scatter. Okay, so this is a scatter plot of the quantiles in two distributions, and you order them. And so you basically plot the quantiles against each other. So it's an ordered quantiles of from two distributions. Okay, so in this case, well, what are the two distributions? Well, one is what we observed in the residuals, and what's the other? Well, it is the normal distribution that we want to compare them to. Okay, so those are the two distributions that we want to use as the quantiles in this plot. Okay, so in our case, so what is this? We have the quantiles from the data. Okay, so we can call these the empirical from the residuals. Okay, which are from our data. Okay, and then the other, and then versus the theoretical quantiles from a normal distribution. So we ask whether the quantiles from our residuals match the quantiles from corresponding quantiles from a normal distribution from the assumed normal distribution. Okay, and so visually, what we will be able to see is if they roughly match. Okay, so if the quantiles roughly match, the points will roughly follow a straight line. So it'll be a 45-degree line, so it's like y equals x line. So the points will be scattered around that, and that's how we can see that the quantiles roughly match, which means that the data and the normal distribution, those distributions line up well. Okay, so if the quantiles roughly match, the points will roughly fall on a 45-degree line through the origin. Now, of course, in practice, when we plot it, it'll be closer to 45 degrees if we like scale the residuals, but otherwise we're looking for a straight line. Okay, so that's like a y equals x kind of line. All right, so with that said, let's give you a couple of examples of what those plots might look like. Okay, so this is what we're saying. So this is so this one is a good QQ plot will look like this. So as a picture. So you have points that. So you basically follow this line, and generally 0 is close to the middle of the plot. So on the x-axis we have the theoretical, so the normal quantiles, and then on the y-axis we have the residual quantiles from the residuals. Okay, so that's a good QQ plot. Now, examples of things that we can detect if there is non-normality in the errors. Okay, so let's give you a few examples. Okay, so sometimes we'll see this sort of shape where it's not quite a straight line. So again, we're looking for major deviations. Okay, so sometimes you'll have some points that are that look questionable, but we're looking for systematic patterns. So for example, this is clearly not a straight line. So we're going to draw a line through it. You notice that you have quantiles and the residuals that are not as spread out as the normal. Okay, so it's going to come out with points that are above the 45-degree line and the for small values, and below the 45-degree line for large values. Okay, so here, so the residuals are less spread out than normal. Okay, so if they're less spread out in, if we were to look at the distribution, actually, I'll just draw a picture. So if this is the normal, then what this so I use red for residual means there's less deviation. So you have more residuals in the center of the distribution, and the tails are lighter. Okay, so this is an example of so the red here would be the residuals. Okay, so this is example of our what we call light tailed. Okay, so you can also have the opposite effect where the residuals are more spread out than would be expected with a normal distribution. Okay, so that'd be the opposite effect. So your points might look like this. So where you have the middle part might follow the line, but then as you get to the tails of the distribution, now you lie under the line, and then you lie over the line, which suggests that the residuals are more spread out. So this is the opposite effect, where the roles are now reversed. So okay, so again, here's my normal, and then my residuals would be have greater spread. So in other words, it has heavier tails than a corresponding normal distribution. Okay, so they're more. It's more spread out than would be expected under a normal distribution. Okay, so that's where you have points below at first, and then you have points above in the right tail. Okay, so here again, this is the residuals are now heavy tails. Okay, and so more spread out than normal. In a similar fashion, you can also detect various kinds of skew in the data. So just to give you an example, so here's an example of skew. So we could have, so let's draw some points. So you could have mostly following the line, and then it starts to bend upwards. Okay, so when you add the QQ line, it looks like this. So then you have more. The residuals are more spread out than normal in the right tail. Okay, so that's gonna in terms of the same picture. So you have a normal. So this one is skewed, okay, to the right, because you have more values, more spread on the right tail than we expected under normal. So you'd be able to detect that with this QQ plot. So you'd have something that might match fairly well, and then it has a longer right tail. Okay, so these are the residuals. So these are right skewed. Okay, so those are examples of things that we can detect with QQ plots that we might not be able to see just by looking at a histogram of the residuals. Okay, so we can detect more subtle kinds of deviations from normal distribution. Okay, so to wrap up all these, so we've talked about all the plots that we can make using the residuals. So just as a concluding point, so if these sets of residual plots, okay, so we talked about four kinds of plots that we can make based on residuals, show violations, then that could affect the validity of for example, of confidence intervals and hypothesis tests that we make from the model. So therefore, it's always good practice to check our model assumptions, and generally in this course, we're just going to focus on these kinds of visual assessments, and there are numerical ways to assess as well, but in practice, generally visuals already tell us more than just calculating, for example, a statistic. Okay, so I will pause now to see if there are any questions. Okay, so it is 11:45. I will do a very quick demo just to show you some examples of residual plots. And I also hope you all had a nice hallowed Eve, so that's why I have this pumpkin over here. So we'll do a quick R demo to wrap up today, so you can see some of these residual plots in action. And then next time we're going to talk about how to address model violations if we see them in these plots. Okay, so I'll be on the computer with you in just a moment. Okay, so this will be fairly short, so let's make a few residual plots just to illustrate what we've talked about today. So the first one, I'm going to pull up the Florida Orange data set, so we're going to load that in. This was just a simple linear regression. We're predicting the number of boxes produced from the number of acres. And so we previously fit simple linear regression model. Okay, so clearly x and y are strongly related, but even from this scatter plot, we see that the variance around the regression line might be larger, right, as the number of acres gets larger. Okay, so let's plot the fitted values versus the residuals. Okay, so I'm going to put the fitted values on the x-axis and the residuals on the y-axis, which I can easily extract from model, fitted model, using these attributes, fitted.values and residuals. Okay, so as we sort of expect, here's the residual plot, and then you can see that this sort of plot shows that we have indeed a non-constant variance. Okay, so the variability appears to increase as the fitted value, for larger fitted values, sigma squared appears to be larger. So it doesn't appear that to be consistent with that all fitted values have the same variability around the regression line. Okay, so this points to a non-constant variance. We can also plot the residuals versus just the predictor. In this case, it's going to pretty much look like the same plot because there's just one predictor. Okay, so it's just, you'll see it's the same plot. It's just rescaling the x-axis. Now it's using acres instead. Now, when you have multiple predictors, then this will look different than just plotting the fitted values. Okay, well here there is no time and space ordering, but just to show how you could plot with the indices on the x-axis. So I can do this. So I'm going to make a vector from 1 to n like this. So 1 colon n, and then I can plot those against the residuals. Here, there's no particular ordering; they're just names of counties. So there wouldn't be expected to be any potential dependence over indices in this case. All right, moving on, we have histograms of the residual. So let's look at the basic histogram. Suggests, okay, well, there's potentially some pretty long tails here. But it's not necessarily clear how badly that is compared to a normal. So what we can do is instead do the QQ plot. Okay, so the command is very simple. We just take the residuals and plug them into the QQ norm command, and that would generate the quanta plot using the normal as the theoretical distribution. Okay, so this is what it looks like, we can. So as I mentioned, like because of the scaling, it's not going to be quite 45 degrees here, but we can add what the corresponding ideal quanta line would be, like I did on the board examples. So I can do that by using the QQ line command on the residuals, and what that will do is we'll add that line I drew onto the plots. Okay, so what we see then is that, well, this matches one of the scenarios that we drew on the board, right? We have the residuals being strongly below the QQ line in the early part of the plot, and then far above it at the right tail of the distribution. Okay, so that picture is still on the plot. On the board here, it's the middle plot where the residuals are heavy-tailed. So there's more spread in the residuals than the corresponding normal, which suggests, as we wrote there, that the residuals are more heavy-tailed and don't follow a normal distribution. Okay, so that's how we can see that in this case, we probably want to do something about these violations, and that's what we're gonna talk about, some strategies for that next time. Okay, and as a second quick example, let's pull up the rocket data from before. So this one had two predictors. It had we were trying to predict the amount of thrust from whether the nozzle is large or small, and the propellant to fuel ratio. So now we have two predictors. Okay, so this was the rocket data. So we have fitted the model, and so let's again plot the residuals and the fitted values together. Okay, so this one is sort of interesting because the fitted values have there's kind of a gap in the fitted value, which is not a problem, but we do want to see whether the spread around 0 is fairly symmetric throughout. And here it looks like for smaller fitted values might have there's not a lot of observations. So again, we don't want to jump to conclusions without too much evidence. So here, we have the spread on the left side is slightly larger than the right, but just by the eyeball test, not egregiously so. So this looks okay to me. We can also plot the residuals versus the predictors. So now there's two of them, the nozzle size, which is just 1 or 0, and then we also have the propellant to fuel ratio. Okay, so this one has no egregious violations here. So let's see if that's also the case with the predictors. Okay, so again, here it seems there might be slightly more variability when the nozzle is small as opposed to when it's large in the residuals, but again, nothing stands out as particularly as violations. Okay, we do the same with using propellant ratio on the x-axis. Okay, and so again, there's not too many points, so you shouldn't jump to we shouldn't imagine stuff that's there when that isn't readily apparent and super obvious. Okay, so yeah, it looks like there's no negative residuals in the middle, but then there's only just a few points, so this is quite possible by chance. Okay, so no really egregious violations here. Okay, finally let's look at the residual plots. So here's a histogram. Again, here the way R chose the breaks, we don't see too much. So more informative would be to look at the quantile plots. So let's look at QQ norm of the residuals. So this looks pretty good, right? The data roughly follow this QQ line. So based on the line, imagine if you have a fat line, it basically goes through everything pretty well. Okay, so there's no apparent violations in this case. All right, and just to conclude, I posted one additional data set on the website and on Learn. So it's called Mystery because we have to figure out well what is actually represented in this data set. So let me load it. Okay, so there are a few unlabeled variables here. Okay, so you have the response, which I labeled y, and then we have 3 predictors. Okay, and so if we don't know what this stands for, we can always look at the pairs plot. So let's plot all the possible pairs. Remember when we were looking at multiple regression, so each of these represents, for example, the plot of y on y against x1 and y against x2, and then it also plots the predictors against each other. Okay, so that looks fine as far as for fitting a linear model. So let's go ahead and do that. So let's fit a regression model of y on these 3 predictors, and we look at summary. So it turns out it is all the predictors are significant, highly significant, and so this looks like a pretty decent model with 3 significant predictors and an R-squared of around 0.5. Okay, so we already looked at it. So overall very significant. So as we learned today, it's always useful to look at plots of the fitted values and the residuals together. And so let's do that as our last thing for today. And so well, here's the residual plot, which well, what do you think of this residual plot? Well, it's well, not particularly a random scatter, as you can see, but it looks pretty much like the picture on the board just a few moments ago. So yes, the mystery was in fact that you can hide, there are ways to hide pictures into regressions. I learned this a while ago in grad school, and just wanted to show you just a fun example of that. Okay, so that's the key message today is using residual plots to assess our model assumptions. There are 4 of them, and we can get a sense of whether there are violations to them by looking at the 4 kinds of residual plots that I showed you today. So I will pause again to see if there are any questions, and then we're going to wrap up today's lecture. Okay, so we will be back on stream on Wednesday, and we're gonna talk about how to address potential model assumption violations.